All right, let's jump straight into this explainer. Today we're going to uncover the invisible mathematical rules governing the fluids all around us. Literally, from the water we swim in to the air we're breathing right now, and even the hydraulic systems that build our modern cities, fluids dictate so much of our physical world. And in this session, we're going to break down exactly how they do it.
To start things off, I want you to think about a really common, seemingly simple question. Why do certain objects achieve buoyancy while others just plunge straight to the bottom? I mean, why does a massive steel cargo ship float effortlessly while a tiny little metal coin sinks instantly? Well, the answer to these everyday mysteries lies entirely in the principles of fluid mechanics.
Here's a quick look at our roadmap for today's explainer. 1. Welcome to fluid mechanics. 2. Density and specific gravity. 3. Area, force, and pressure. 4. Depth and hydrostatic pressure. 5. Pascal's principle and hydraulics. And 6. Buoyancy and Archimedes Principle. Let's get into it.
Section 2. Density and specific gravity.
Okay, so density. It isn't just about an object's overall weight. It's really describing how closely packed the atoms or molecules are within a specific given volume. In physics, we represent density with the Greek letter rho. You calculate it simply by dividing mass by volume. So, heavier, tightly packed atoms, that means you're dealing with a much higher density material.
It's actually wild when you look at the sheer variety of fluids we deal with in physics. Just look at this list. You have fresh water sitting at a clean 1,000 kilograms per cubic meter. But then compare that to mercury, which is an incredibly dense liquid metal we use in things like barometers. And on the flip side of that, we have gases, like air, which are highly compressible. Really understanding these baselines is basically step 1 in mastering fluid mechanics.
Now, sometimes throwing around those raw density numbers gets a bit clunky. So instead, we often want to compare a fluid directly to our most common reference point, which is water. To do this, we use a dimensionless ratio called specific gravity. It is simply the density or specific weight of whatever substance you're looking at divided by the specific weight of water. It's a fantastic shortcut.
Let's actually walk through this step by step so you can see how to calculate the specific gravity of a really common fluid, like SAE motor oil. First, we establish our volume. Let's say we have a quart of oil, which is 0.0334 cubic feet. Now, that specific volume weighs 1.85 pounds. Dividing those gives us a specific weight of 55.4 pounds per cubic foot. Since water is roughly 62.4 pounds per cubic foot, we just divide our oil's 55.4 by the water's 62.4. That gives our oil a specific gravity of 0.888. And because that number is less than 1, we know, mathematically for sure, that this oil will float on water.
Moving right along to Section 3, area, force, and pressure.
So, what exactly is pressure? Well, it's just the applied force divided by the area that it's acting upon. We measure this in units called pascals, which are exactly equal to 1 newton of force per square meter. Now, solids exert pressure downwards due to gravity, right? But fluids are special. They uniquely apply pressure in absolutely every single direction.
101,325 pascals. That massive number is the average atmospheric pressure pressing against you from every single direction right now, assuming you're at sea level. Crazy, right? You don't actually feel it only because the fluids inside your own body are pushing back out with that exact same pressure.
All right, Section 4, depth and hydrostatic pressure.
You know when you dive down deep in a pool and your ears start to ache? Well, the deeper you go in a fluid, the more fluid is physically stacked directly above you. All that extra weight presses down. This means pressure increases based strictly on 3 variables: the fluid's density, the downward pull of gravity, and the depth of the fluid column. In physics equations, we define this as P equals rho times G times H. Let's put some numbers to that swimming pool example. If you're swimming just below the surface, say a quarter of a meter down, and then you dive to the bottom of a 3-meter deep pool, your change in depth is 2.75 meters. This mathematically explains the ear popping. You multiply the water's density, which is 1,000, by gravity by your 2.75 meter depth change. Boom! Suddenly your poor ears are dealing with an extra 27,000 pascals of pressure.
Section 5, Pascal's Principle and Hydraulics.
Okay, so back in the 1600s, this French physicist named Blaise Pascal figured out a monumental quirk of physics. He realized that if you have a confined fluid, meaning it is trapped and has absolutely nowhere to go, and you apply pressure to it, that fluid transmits the applied pressure equally in all directions. This one simple principle is the entire secret behind massive, heavy hydraulic machinery.
Picture this. You have a mechanical setup applying force to a piston on the left side of a tube. That piston pushes the fluid, but because the fluid is trapped and essentially incompressible, it instantly transmits that exact same pressure all the way through the tube to push up on a second piston over on the other side.
And this is where it gets incredibly cool. This is the literal magic of physics. Let's say you apply 10,000 pascals of pressure to an input piston that has an area of 1 square meter. That's 10,000 newtons of force. The fluid transmits that 10,000 pascals perfectly to the output piston. But what if we engineer that output piston to be bigger, say an area of 2 square meters? We know pressure equals force over area. So 10,000 pascals acting on 2 square meters equals 20,000 newtons of output force. By simply widening the area of the output piston, we literally double our lifting force without putting in a single ounce of extra effort. That right there is exactly how a mechanic can so easily lift a 2-ton car.
And finally, Section 6, Buoyancy and Archimedes Principle.
You've probably heard the legend, right? The Greek scientist Archimedes was tasked with figuring out the density of a king's crown. While stepping into a bath, he noticed the water level rise, and he had this massive realization, one that supposedly made him run naked through the streets yelling, "Eureka!" He realized that an object pushes away or displaces a volume of fluid exactly equal to its own submerged volume. This displacement creates a difference in pressure that results in a net upward push, and we call that upward push the buoyant force. So, bringing it back to that question from the very beginning of the explainer, if we place a billiard ball in water, it displaces a specific amount of liquid. But because solid resin is way denser than water, gravity pulls it downward with much more force than the upward push of that displaced water, so it sinks like a rock. But a hollow racquetball? It's less dense than water. The buoyant force pushing up easily overpowers the downward pull of gravity, popping it right back up to the surface. So, let's wrap this whole thing up. What are the big takeaways? Fluids exert pressure in all directions. Whether an object sinks or floats is just a mathematical battle between its density and the fluid's density. Hydrostatic pressure climbs the deeper you dive. Confined fluids allow us to actually multiply force using Pascal's principle. And Archimedes taught us that the buoyant force holding up massive steel ocean liners is simply equal to the weight of the water they push out of the way.
I'm going to leave you with this final thought to chew on. Knowing the sheer power and mathematical elegance hidden inside a simple glass of water, what incredible engineering breakthroughs are waiting to be discovered next? Keep questioning, keep calculating, and I'll see you in the next explainer.